we are going to see applications of Pascal's law. Applications of Pascal's law. First application, hydraulic lift. Hydraulic lift. It is used, here you see, it is used to lift a heavy object using a small force, and it works on the principle of Pascal's law. Hydraulic lift. Now we will consider, suppose this is diagram of the hydraulic lift. S1 and S2, see here, this S1 and S2 be the two pistons. S1 and S2 be the two pistons. S1 has area of cross section A1. See here, S1 has area of cross section A1, and S2 has area of cross section A2 such that A2 greater than A1. Now F1 is force applied on S1. See here, F1, this F1 is force applied on S1, and we consider F2. Here we get upward force due to the piston S2. F1 is force applied on S1 in downward direction, and F2 be the outward force on S2 we get. Now here F1 is force applied on S1 and BQ. Here we consider P1 is pressure in this first cylinder having area of cross section A1, and P2 be the pressure in the second cylinder having area of cross section A2. Then we can write here P1 is equal to, I will write here F1 upon A1, and P2 be the pressure in second cylinder. We can write here P2 is equal to F2 upon A2. Now according to Pascal's law, these both pressures are equal. I will write here P1 equal to P2. You give reason, Pascal's law. Now we put these values of P1, P2 here. Then we get here F1 upon A1 is equal to F2 upon A2. And if we solve this, then we get here F2 is equal to, suppose I will write here like this, F1 into A2 upon A1. Now F1 is the applied force in downward direction on this S1 piston, and F2 be the that is the resultant force, or we get effect of this force F1. Force F2 is on S2 in upward direction. Then F2 is equal to, we get here F1 into A2 upon F1. Whatever may be the force F1, but this ratio A2 upon A1 is, this ratio A2 upon A1, this ratio is greater than 1 because A2 is greater than A1. If we increase this ratio A2 upon A1, then F2 increases, and F2 is much larger than F1, and heavy load can be placed on S2 and can be lifted up or moved down by applying a small force. This is the construction of hydraulic lift. I hope all you understand this. Now we will consider next application. Application number second. We consider here application number second, hydraulic brakes. They are used in cars or vehicles. See here, suppose I consider another diagram. Suppose this is the diagram of this. You see here, this is a block diagram. Here we consider these A2. Here we consider again A2, and we consider here A1, this cylinder. these 1, 2, 3 and 4, these are, we call it as a slave cylinders. There is a brake fluid in these cylinders. All is the fluid, brake fluid. And we consider this is the master cylinder whose area of cross section is A1. And these tubes, see here, these tubes, they are hydraulic tubes. Now, this is the master cylinder, these 4 are slave cylinders. These are hydraulic tubes. This is hydraulic fluid, brake fluid we consider. And here to this master cylinder, brake pedal is placed. Brake pedal is fixed. And F1 is the force applied on brake pedal. And we get, due to the Pascal's law, we get here, see here, this F2. These are the forces we get on the slave cylinders. Now here A1 is area of cross section of master cylinder and A2 is area of cross section of slave cylinders, and here you get A2 greater than A1. This is the arrangement in the vehicles. Now whenever brake pedal is placed by a small force F1, then we get F2, a force which is large, which can stop the that is the vehicle. Any vehicle that is lighter or heavier vehicle can be stopped by using this brake pedal. Again, we consider A1, A2, these are the areas. A2 very greater than A1 we can write. Suppose F1 and F2, these are the forces. Then we can write here, like previous article, F1 is equal to PA1 and F2 is equal to PA2, because totally inside this brake fluid pressure is constant. Now we can write here P is equal to F1 upon A1 and here P is equal to F2 upon A2. And if we compare this, then we can write here F2 upon A2 is equal to F1 upon A1, and therefore F2 is equal to A2 upon A1 into F1. That means depending on this ratio, A2 upon A1, this is much greater ratio, and depending on this ratio, small force F1 into this big ratio creates a large force F2, and by that large force a vehicle can be stopped. These two are the applications of Pascal's law. I hope you all understand this. Now, depending on this Pascal's law, many, that means we consider JCB, tractor, or all other that is cranes, they are arranged, and these all are applications of Pascal's law. Now we start another article. Measurement of pressure. Measurement of pressure. Measurement of pressure. Now here we consider instrument used to measure pressure are called as pressure meters. Pressure meters or pressure gauge or vacuum gauges. These are names. Now we will consider to measure pressure. First we will consider instrument. First instrument we consider, that is a mercury barometer. Mercury barometer. Now in this mercury barometer we consider here, that is this is a barometer which is created by using a mercury. This instrument measures the atmospheric pressure, so we call it as a barometer. Now we consider here, suppose this is the container. And in this container mercury is placed. Suppose this is the mercury, hole is the mercury. Now here we consider another, a glass tube of 1 meter length. We consider a glass tube of 1 meter length and 1 cm of diameter. Small glass tube of 1 meter length and 1 cm of diameter is completely filled by mercury, and quickly inverted into small dish or small container containing mercury. Now the final arrangement is like this. See here, this is the tube, which is filled by mercury and quickly inverted in this. Now what happens here? Mercury levels falls down, and here we consider, suppose this is the mercury, and here mercury level falls down, and in this region there is a creation of vacuum. We call this vacuum as Torricelli vacuum. Torricelli's vacuum. This is the vacuum. Now here we consider point B and C are, we consider, suppose points. Here this point is A, this point is B, and this point is C. Points B and C are at same height, but one is inside the capillary and one is outside the capillary. But the surface of mercury at point C, P0 is the atmospheric pressure. Here you see, P0 is the atmospheric pressure. Atmospheric pressure at point C. P0 is the atmospheric pressure at point C. Now here Pa equal to 0. Pa is equal to 0. Therefore we can write here Pb is equal to P0. Pb equal to P0. This is the pressure, and therefore Pb is equal to, I can write here, Pa plus H rho G. This is the pressure at point B. Pb is equal to Pa plus H rho G, and here we consider Pa is equal to 0. Therefore I will write here Pb is equal to H rho G is equal to P0. This is the mercury barometer. Now we will consider next barometer, that is second type of barometer, that is we consider here second barometer, that is open tube manometer. See, open tube manometer. Here in this open tube manometer, suppose I will draw a diagram like this. Suppose this is the U-tube, now this is the U-tube, like this. This is the U-tube, and one end of the U-tube is open, and other end we consider here like this arrangement, that is a sphere we consider, that is container we consider. Suppose this spherical container, dB the spherical container. Now we consider mercury is filled in this tube, then we get this type of height difference here, that is A point is here and we consider C point is here, and mercury is in this U tube like this. This is the arrangement. And this height difference, see here, point C is at this height, and this height difference is H. Here point A, at point A, because this is point B and this is point C. If Pa is the atmospheric pressure at point A, Pa is the atmospheric pressure, and we consider here Pb is equal to Pc, and here we can write here Pb is equal to Pc plus H rho G, and therefore we get here P that is a pressure Pc is at, we consider here, that is a pressure, therefore P is equal to P0. This pressure is P0. atmospheric pressure P0 plus H rho G. This is all about the open tube manometer. I hope you all are understand all this. Thank you.